Hello, welcome to the Day 13 Notes, Section 6-7, Roots and Zeros. Today what we're going to be doing is determine the number and type of roots for a polynomial equation, as well as find the zeros of a polynomial function. So this is the last day of notes in the chapter. However, there is one more section. But because we are going to be doing everything on our calculators, or the majority of the work is going to be done on our calculators, for us, 6-7 and 6-8 become the same section, so we're not going to do notes on 6-8. Okay, so the first thing we're going to do is define zeros, factors, roots, and x-intercepts. And as you see here, I already drew a graph of a polynomial function so that I could refer to specific things in this graph as they are described here. So if c is a 0, that means the same thing as c is a root, which is then, that means x minus c is a factor, and then c comma 0 is an x-intercept. So notice that I made this graph cross the x-axis at -3 and +2. So we could say that -3 and 2 are zeros. They're zeros of that function. We could also say that -3 and 2 are roots. Again, those mean the same things. So now, if -3 and 2 are zeros, if you go backwards from how we solve with factoring, that makes x plus 3 a factor, because if I had to solve that, I would get x equals -3 if this equation equals 0, and then also x minus 2 is a factor. And then finally, c comma 0 is an x-intercept. So, I mean, that makes sense. This ordered pair right here is -3, 0, and this ordered pair right here is 2 comma 0. So those are both x-intercepts of the graph. All right, fundamental theorem of algebra. A polynomial equation with n degree, n being any number, has exactly n roots. So whatever the degree is, that's how many roots or zeros that it has, and they could be repeated, meaning you'll have a 0 of 2 twice, or they could be imaginary. So for example, if you look at this first polynomial, it's 2x cubed minus 5x squared plus 2. It would have 3 roots because the degree of this polynomial is 3. That means it has 3 roots. The next one, -3x to the 14th minus 2x to the 8th plus 5 would have, you look at the degree, it's 14 degrees, so it would have 14 roots. So whatever the degree is, that's how many roots, aka zeros, you're going to get. An even function has an even number of roots, and an odd function has an odd number of roots. Okay, so for our first example here, we're going to state the number and type of roots. And the way we would do that is we have f of x equals x to the 6th minus 10. Hopefully you realize that x to the 6th, because that degree is 6, it has 6 roots total. So the way that we're going to figure out the type of roots that it has is you're going to plug this equation in on your calculator, and you would get the picture that I have here. Kind of looks like a parabola, and you look for where this graph crosses the x-axis. So it crosses here and it crosses there. We do not care that it crosses the y-axis. That is not a root. A root is only where it crosses the x-axis. So that is the number of real roots that there are. So in this case, there are 2. So now, by process of elimination, if there's 2 real roots, and in the beginning we said there's 6 roots because the degree is 6, so that would mean with 2 being real, 4 have to be imaginary because we need 6 total roots. Again, we could see physically on the graph the 2 real ones, again where it crosses the x-axis. We know there's 6 roots total, 4 must be imaginary. Okay, I would like you to try example B on your own. You're going to type into your calculators into y equals, you're going to type this function, it's x to the 5th minus 5x to the 3rd plus 2. So you're going to press graph after you type the equation in, look and see how many times does this graph cross the x-axis. Then I want you to sketch the graph, what you see on your screen, and then tell me how many real roots there are. Again, that's how many times it crosses the x-axis, and then subtract to figure out how many imaginary roots there would be. Okay, so for this one you should have gotten that there's 3 real roots, 2 imaginary. I didn't sketch the graph for you. I will be checking that tomorrow when I check in your notes. So the first day of tomorrow's classwork, you're going to have problems where you're going to have to solve, and many of them are going to be able to be factored in the beginning, but later on you're going to get polynomials that can't be factored. So you're going to have to find all the zeros in a different fashion. So let's start with this first example. We have x to the 3rd plus 2x squared plus 9x plus 18. Step 1, type that into your calculator. Step 2, look at the graph. And when you look at the graph, step 3, what you're going to be doing is you're going to press second trace calc, and we are going to be calculating a 0. So again, this is where it's asking you for a left bound, right bound, and a guess. And then step 4, you will see that your calculator will tell you what the 0 is. Now what you do with that 0, in this case there's only one real 0, which means, looking back to the equation, it was an x to the third, there will be two imaginaries. So we have to find those two imaginary zeros. The way you do that is you are going to take that 0 and you're going to do synthetic division on this original polynomial. So on the outside I put the 0, which is -2, that's what I found with my calculator, and then across the top the coefficients of the polynomial, so 1, 2, 9, and 18, and as always you are making sure that there are no placeholders of 0 that you have to put there. Now because -2 is a 0, I know that my final number here should be 0. If I get anything else, that means I made a mistake somewhere along the way, so go and check your work there. So bring down the 1, multiply 1 times -2, we get -2. 2 plus -2 is 0. 0 times -2 is 0. 9 plus 0 is 9. And then -2 times 9 is -18. And when I add those two, I do get this 0, which means I did synthetic division correctly. So now the second thing I'm going to do here is take these numbers and rewrite this polynomial. And because we started with an x to the third, this becomes x squared. There's 0 x's, and then plus 9. And then whatever that polynomial is, you equal it to 0. Now, you always want to keep doing synthetic substitution until you get down to an x squared. So we started with an x cubed. It only took one synthetic substitution or division to get us to an x squared. If we started with an x to the fourth, when we do synthetic one time, it brings us down to an x cubed. You would have to do it one more time to get to an x squared. So this x squared plus 9 cannot be factored, but I can solve it. It's going to be x squared equals -9, giving us, when we square root both sides, x equals plus or minus the square root of -9. We cannot leave a negative underneath a radical, so we simplify that. It's x equals plus or minus 3i, and then that -2 that we got from our calculator. And those are the three zeros. So again, remember, if we started with a cubic, something to the third degree, we're going to get 3 zeros. When you look at the graph, you see that there's one real 0. Doing synthetic division gives us a polynomial that we could then solve and get the two imaginary zeros. For example 3 here, we have f of x equals x to the fourth minus 6x cubed plus 6x squared plus 24x minus 40. Type that into your calculator, press graph, and hopefully you do see that there's two real zeros here, right there and right there. You are going to use your calculator to find those two. So now we're going to have two real zeros at 2 and -2, which means there's going to be two imaginary that we have to find. So what we're going to do is synthetic division. You could use either one of the zeros. If there's more than one real 0, it doesn't matter which one you start with, because you will still get the final answer is going to be the same. So 1, -6, +6, 24, and -40. And again, because this is a 0, I have to end up with a 0 at the end. If I have any other number there, that means somewhere along the way I either added or multiplied incorrectly. Bring down the 1, multiply, you get 2. -6 plus 2 is -4. -2 times -4 is -8. Adding, we get -2. Multiplying, -4. Adding, we get 20. And then multiplying, we get 40. Add those two, we do get 0. Now, because the polynomial that I started with was an x to the fourth, if I was to rewrite this one, I would have x to the third minus 4x squared minus 2x plus 20. Remember, I have to keep doing synthetic until I end up with the x to the second. So this still, if you think about it, is still an x to the third polynomial. I have to make it x to the second, and the way I do that is I do synthetic again, but I do it with the next 0. So I would take -2, and then I use these numbers from this row and put those across the top. So 1, -4, -2, 20. I have to end up with a 0 here at the end. Bringing down the numbers, I get 1. Multiplying, I get -2. -4 plus -2 is -6. negative 2 times negative 6 is positive 12. Negative 2 plus positive 12 is positive 10. Multiplying 10 times negative 2, you get negative 20. And that does give me 0, which is an excellent sign. Now, I do like I did in example 2, where I brought it down to an x squared. So I'm going to rewrite this polynomial. I'm going to do this over here. X squared minus 6x plus 10, and I equal it to 0 because I am solving for the zeros. Check if this could be factored. So we're looking for factors of positive 10. That would add up to negative 6. The only factors of 10 are 1 and 10. The bigger one would have to be negative. And 2 and 5. This doesn't work. This doesn't work. So remember that any quadratic can be solved. Just because this cannot be factored doesn't mean it doesn't have a solution. It does. It just means we have to do the quadratic formula. So let's go ahead and do that on this problem. We're going to get x equals opposite of b, so 6, plus or minus the square root of b, which is negative 6 squared, minus 4ac. And that's all over 2a, a being 1, so we just put it over 2. All right, let's clean this up. X is going to equal 6 plus or minus the square root of, remember that if you just type in a negative 6 and squared on your calculator without the parentheses, your calculator will tell you it's negative, but negative 6 times negative 6 is positive, so you do have to put that into parentheses. And then so it's 36 minus 40 over 2. Cleaning that up, we get x equals 6 plus or minus the square root of negative 4 over 2. At this point, some of you might be tempted to simplify and reduce this fraction. However, you can't because some things are inside the radical, some are outside, so you can't do that yet. But we are going to simplify this over here. So it's going to equal 6 plus or minus square root of negative 4 is 2i over 2. Now that I have all of them released, I can simplify, and it becomes 3 plus or minus I, and that's it, because I could take a 2 out of all of them. So remember, our original function was raised to the 4th degree. That means it has to have 4 roots. Here are 2 imaginary. One of them is 3 plus I. The other one's 3 minus I. And then our ones that we got from our calculator, 2 and negative 2. And if you want, you could write that shorthanded, plus or minus 2. It's the same thing as 2 and negative 2, writing it separately. Example 4 here is a stop problem that I want you to try on your own. So remember, here's what you're going to do. You're going to type this into y equals. So you're going to type in x to the third plus 6x plus 20. You're going to look at the graph and find the real zeros. And because it's an x cubed, you only have to find one real zero before you get it down to an x squared. Once it's an x squared, don't use your calculator anymore. Either factor it or do quadratic formula. So one thing that I'm going to give you a heads up on is when you find that 0 using your calculator, that number is going to go in here. Notice that there is a missing term, so you're going to write 1 and then that 0 placeholder, 6 and 20. You're going to end up with a 0 here at the end. If you don't, that means you didn't do it correctly. And then you are going to have to do quadratic formula to find the other 2 zeros. So go ahead and pause the video and please do this problem. Alright, so for this problem you should have gotten x equals 1 plus or minus 3i and negative 2. Remember that plus or minus is just a shorthanded way to write 1 plus 3i, comma 1 minus 3i, and then negative 2 is what you should have gotten on your calculator. Remember that tomorrow's classwork, you're not going to have to do this for all the problems. The first few where you're finding zeros will be ones that you could factor and then use zero product property or quadratic formula to find the zeros. Alright, so the final thing that we're learning in this chapter is to write polynomial equations given the solutions. And the one thing that's really important here is the complex conjugates theorem. And that's saying if a plus bi, so if you have some imaginary number, if that's a 0 of the polynomial, its conjugate, meaning you're going to switch the sign of the imaginary part, is also going to be a 0. So we are going to write a polynomial with integer coefficients that has solutions of 4, negative 3, and 5. So what we're going to do is if 4 is a solution, that means one of the factors was x minus 4. If negative 3 is a solution, that means x plus 3 was a factor. And if 5 is a solution, that means x minus 5 was a factor. Because thinking backwards, when we normally factor, we get it into the factored form. You set each factor equal to 0, solve for x, and we would have gotten 4, negative 3, and 5. So now what I want to do is multiply these three binomials together. So you could do the boxes if you want, you could do FOIL, but we're going to multiply two of them at first. So I'm going to take the first one and the second one. I'm going to multiply those two together. I get x squared minus 4x, a 3x, and a negative 12. So combining like terms, I'm going to get x squared minus x minus 12. Now remember, what I've done is I've multiplied these two together. I still have to take this trinomial and multiply it by x minus 5, so I could do a table again where I'm going to list x squared minus x minus 12, and I'm going to multiply it by that remaining x minus 5, and I would get x to the third, because we add exponents, minus x squared minus 12x minus 5x squared plus 5x, or positive, I didn't have to write that plus sign there, and then a 60. Alright, let's combine these terms. We're going to get x to the third, because there are no other x to the thirds. Negative 5x squared minus 1x squared is minus 6x squared. 5x plus negative 12x is minus 7x, and then plus 60. Now make sure that your answer makes sense to what they gave you. They gave us 3 zeros, 3 solutions. That means we had to have a third degree polynomial, and we do. So this is our final answer. All right, let's take a look at example B. Now, I want you to add a comma here between the 1 and minus 3i. So they gave us the zeros of 1, negative 3i, and negative 2. Now, up here, remember the complex conjugate theorem, i's always come in twos. So if negative 3i is a 0, that means positive 3i will also be a 0. They don't list them, but you have to know that i's, just like in nature, come in twos. So here is how I would write this out. If I have a 0 of 1, that would be an x minus 1. And then I'm actually going to write my two I values together. So x minus 3i and then x plus 3i. And then if negative 2 is a 0, that would mean the factor is x plus 2. And I should really write f of x here. Alright, what I'm going to do is multiply these two together first. So I'm going to have x minus 3i, and then x and a positive 3i. For my table, I would get x squared minus 3ix, here's a positive 3ix, and a minus 9i squared. Combining like terms, I get x squared, the 3ix's cancel because one's positive, one's negative, and then minus 9i squared. Please remember from chapter 5 that I squared is equal to negative 1. So I'm going to replace that with a negative 1, and I get x squared plus 9. What I'm going to do here is rewrite this f of x that I had originally written in black, and I'm going to rewrite it now with those two imaginary roots multiplied together. It's x minus 1. Now instead of x minus 3i, x plus 3i, I found that when I multiply those two together, it's x squared plus 9 and x plus 2. Remember when we were solving, if I was to set the first factor here, x minus 1 equal to 0, I get that 1, 0. If I set this equal to 0, I would have to subtract 9, so I'd have x squared equals negative 9. When you take the square root, you would get that plus or minus 3i, and that's how it works every time, and then I have this x plus 2. Once you do this, now it becomes like example, or the first example, A. I have to multiply 2 together and then multiply in that last one. So I'm going to take x minus 1 and multiply it by x squared plus 9. So I'll do the little box, and I get x to the third minus x squared, a positive 9x, and a negative 9. Notice there are no like terms there, so this is just going to be x cubed minus x squared plus 9x minus 9. And I'm not done yet because I still have that x plus 2 hanging out at the back end, so I multiply the first two together, and I'm going to multiply that x plus 2 in there. So that will give me, I start off with my x cubed minus x squared plus 9x minus 9, and I multiply that by x and 2. And do the multiplication. So I would get x to the fourth minus x to the third plus a 9x squared minus 9x, and then I have 2x to the third minus 2x squared plus 18x. I don't know why sometimes I write that plus, doesn't make a difference. I could, anytime it's positive, I could write that plus. And let's combine like terms. X to the fourth has no one to be combined with, so it's just x to the fourth. I have a negative x to the third and a positive 2x to the third, leaving me with an x to the third. A negative 2x squared with a positive 9x squared is going to be a positive 7x squared. And then 18x minus 9x is plus 9x. And then finally minus 18. Again, in the beginning, they gave me 3 zeros. However, i's always come in pairs. So that means if negative 3i was a 0, positive 3i is a 0. So really, this thing had 4 zeros. It's an x to the fourth. So my answer matches the number of zeros that it should have. And again, I do want to stress that it doesn't matter what order you multiply these in. You'll always get the same answer. So even here, once I got that x squared plus 9, I could have taken x minus 1, multiplied it by x plus 2. I could have multiplied those two together first and then multiplied it by x squared plus 9. The order doesn't matter. I just went left to right after the i's. Okay, for the last example of the chapter, I would like you to try it on your own. We have 2 zeros given here, for I and 2. However, keep in mind that if I give you a 0 for I, i's come in pairs, so there is that additional 0 in there. So go ahead and try that and check your answer against mine. Alright, the answer you should have gotten is x to the third minus 2x squared plus 16x minus 32. Remember that whenever you have a 0 that has an I in it, you're going to have another I 0 in there. You will end up with an I squared. Please do not forget when you are doing these problems and there's an I given to you as one of the solutions, one of the roots, one of the zeros, please don't forget that when you multiply together, you will end up with an I squared that has to be replaced with a negative 1, or else you may get stuck and not know what to do, for the rest of the problem. All right, thanks for watching. Have a good one.